Welcome back, dear students. Today, in this lecture, we are going to start a new topic, that is limit state of collapse, compression. Till now, we had discussed on limit state of collapse, flexure, limit state of collapse, shear, limit state of collapse, torsion. Now we are going to start the limit state of collapse, compression. Primarily designed to take the compressive forces, that is, the RC structure will be primarily designed to take the compressive forces. In most of the cases, compression is accompanied by flexure also. That is, it will experience flexure also. There will be bending because due to eccentric loading, there will be flexure also taking place in the structure. Most common compression members are, that is, the most common compression members that we consider for the design of RC structure are column and struts. So I will discuss in detail what do you mean by column and a strut. Column means this vertical member. This vertical member is called as a column, and when it is inclined, it is given as a brace. When it is inclined, then it is called as a strut. That is, the vertical member constitute a column. Here the load will be applied from the top, and this will be under compression. And here the vertical inclined member, here the load will be applied from the top or from the side. It will also take compression, and it is called as a strut. So you can see the schematic representation. This is actually a steel structure. This you can see the column here, the horizontal member, that is a beam, and this is the vertical inclined member that is taking compression, that is the strut. Here the load is being applied. So this member and this column will be under compression due to the load which is being acted upon here. So I can conclude, when a member carrying mainly axial load is in vertical, it is termed as a column, while if it is inclined or horizontal, it is termed as a strut. So that is the basic difference between a column and a strut. Now you can see the load transfer mechanism here. The load which is being applied here is distributed towards the beam from the slab. From here, the slab, you can see the load is getting distributed to all the sides, and from the slab it is being transferred to the beam. From the beam it is getting transferred to the column, and from the column it is getting transferred to the footing, and the footing will exert the reaction, and this is the soil. So till now we have studied the design of a slab, design of a beam. Now you are going to study the design of a column. In the next semester you will study the design of a footing, which means you will completely study the design of a building. So in the next semester you will deal with how to design a whole building. Before that, you need to understand how to design the individual components of a building. So now you are going to discuss mainly on the design of an RC column. Okay. So the reinforcement pattern in a reinforced column. Generally in a column, the main reinforcement is provided in vertical direction. As you can see here, see the reinforcement here are in vertical direction over here. That is, the columns are placed vertically, and the longitudinal or the main reinforcement are placed vertically in a column. You can see here it more clearly. The column is here. The reinforcement are going vertical. The longitudinal reinforcement are vertical. It is exactly opposite to the direction of a beam. Now the lateral reinforcement is also provided to keep the main reinforcement position. You can see this is your main reinforcement. This is a main reinforcement, and the lateral reinforcement are provided. You can see the lateral reinforcement. In columns, we call this as lateral reinforcement. In beams, we provided shear reinforcement or lateral reinforcement. Here it is called as lateral reinforcement or lateral ties. This is called as lateral ties. Okay. So this is a reinforcement pattern in a RC column. The remaining will be filled with the help of concrete, and the minimum clear cover provided for this column is 40 mm, that is 4 cm. We will provide a minimum cover, a nominal cover of 4 cm for column. Now you can see another view of this column. This is the main bar going like this, and now this is the lateral stirrups or lateral ties provided. This is actually given for the confinement of this main reinforcement. Otherwise, when we pour this can get buckled. We will study in detail of the use of this lateral ties. Now, functions of the longitudinal reinforcement or the main reinforcement. To take the vertical compressive load, obviously this is given to take the vertical load which is coming on the structure. Some part of the load will be taken by the concrete, and as well as some part will be taken by the reinforcement. To resist the tensile stresses in the column due to eccentric load, moment or transverse load, that is, if the load acting is eccentric, then definitely there will be a moment arising, or if the load itself there is a moment, uniform moment or a concentrated moment acting, then also there can be a tensile stress in the column, or due to transverse loading. Transverse loading means due to horizontal loading in a column there can be a tensile stress occurring in the column, and that has to be taken by the reinforcement because the concrete is very weak in taking tension. There is, you can see here when there is an eccentric loading due to this load is actually, I'll show here, this load is actually an eccentric load. If it was acting exactly at the axis, then it could have been a axial load, then there will not be any moment. But here see, there is an eccentricity E. This distance is E from the center of the axis. As a result, there will be this. I can resolve this into, I can change this into a, this is equivalent to a direct load P and a moment P into A. And as a result, this is going to deflect in this way. This is going to deflect in this way. This is going to deflect in this way. And here you can see there is, due to this load P and moment M is equal to P into E, you can see here there is compression, and at the outer face there is tension. And if we are not providing reinforcement to take this tension, what happens is this concrete cannot take the whole tension which is happening here. The concrete will not resist the tension. So we need to provide the reinforcement. We will be providing the reinforcement in this way. That is, we will be providing the reinforcement such that this tension can be taken. This tension can be taken. So that is, here the main reinforcement is to resist the tensile stresses in the column due to the eccentric load. It can be due to an eccentric load, or if it is a moment directly acting. Suppose a moment is there directly, or if there is a transverse load. If there is a transverse load acting, then this has to be resisted by the longitudinal reinforcement. Now the next one is to prevent the sudden brittle failure of column. Definitely, when you are providing the reinforcement, what happens is that the structure will become more ductile, so that the sudden brittle failure of the column can be avoided. To impart the ductility to column, definitely when we are providing reinforcement, ductility will be introduced or will be increased. Functions of transverse reinforcement, you can see here. The transverse reinforcement means this is your longitudinal reinforcement, and we will provide the reinforcement in the form of rings, and this is called as transverse reinforcement. If you see the longitudinal section, you can see like this. This is a cross section, and this is a 3D view. This is a 3D view. This orange colors are the your main reinforcement or longitudinal reinforcement, and this one constitute your transverse reinforcement. So the functions of the transverse reinforcement, the main function is to prevent the longitudinal buckling of the reinforcement. Buckling means when I am applying a load from this top, this has a tendency to come like this. This will come like this. It has a tendency to go like this. So if no lateral ties are provided, then the longitudinal reinforcement has a tendency to buckle. Only during ultimate stage, when the cover falls off and the reinforcement is exposed. That is, what happens is that when I am applying a load from the top, what happens? This, if the lateral ties are not provided, due to the length of this will buckle in this way. You can imagine like this. We are applying a load on a refill. You are having a pen refill. You are applying the load. What happens? It will deflect in such a way that is called as the buckling. Similarly, what happens if no lateral ties are provided? This will happen, and this occurs due to occurs during the ultimate load condition, or when the load is increased to a certain stage. At that time, what happens is that the concrete will fall off. The concrete cover falls off because this will try to move in this direction, this horizontal direction. The concrete cover will fall off, and as a result, there will be swelling of concrete, and the reinforcement will be exposed. And this the column cannot take much load if we are not providing the transverse reinforcement. Second one is to confine the concrete, thereby preventing its longitudinal splitting. That is, this will confine the concrete or the main concrete inside this like a cage, and as a result, it won't split, it won't fall off. To impart ductility to the structure, that is, it will impart ductility to the structure of the concrete to prevent sudden brittle failure of the column. So that is the function of transverse reinforcement. Now the next one is classification of column. First one based on the cross section, that is circular column. You can see based on this it is called a circular column. This cross sectional type, this is called a circular column, and here we need to provide a minimum of 6 longitudinal bars for a circular column. You can see the ties are provided like this, lateral ties are provided like this. So based on the cross section, the first one is circular column, second one is square column. You can see this is square column. Next one is a rectangular column. So most of the cases we will be providing these three, either circular column or rectangular column or square column. And in other cases for architectural purpose we may provide hexagonal or pentagonal shape, etc. It can be E shape, T shape, I shape, etc. That is based on the architectural concept, and if the structural designer tells that you need to provide this, we will go for that. Now based on the type of transverse reinforcement, that is based on the type of transverse reinforcement, the first one is tied column. Tied column means, you can see here, this is a column, you are providing the lateral reinforcement or transverse reinforcement in the form of ties. This is called as ties and this is called as lateral ties. Then here you can see this is in the form of circular ties and this is form of square ties. Then if the transverse reinforcement are provided in the form of lateral ties, then the column is called as a tied column. That is, if you are providing lateral ties, then it is called as a tied column. Next one is spiral column. That is, if you are providing the transverse reinforcement in the form of spirals, you can see here, one bar starts from here, it is going throughout, it's like this, it's going like this. It goes up to the length of the bar, it goes like this. This is called as a tied spiral column. And if you take a cross section over here, you can see the spiral like this. This is a cross section taken longitudinally at the midsection. You can see the like this, and this is the another cross section. So this is, you can see there is a small mistake here. You require at least 6 number of bars for a circular column. There should be 2 more bars here. So I took it from the net, so there should be 2 more bars here. Okay, there should be minimum 6 bars for a circular column. The spiral column means if the lateral reinforcement is provided in the form of helix, then the column is called as a spiral column. The advantage of this column is that ultimate load, it can take somewhat more load than the tied column. It can take somewhat higher load than the tied column. It will take approximately 5% more load than your tied column. That is, during the initial stage, the tied and the spiral column behaves alike. At ultimate stage, the spiral column provides better confinement. That is, this spiral helix will provide better confinement to the concrete, and hence it will carry higher load, and approximately it will carry 5% more load than your tied column. That we will study when the design of an helical reinforced column. Okay. Now, third one is composite column. This composite column means you will have your longitudinal reinforcement, you will have your lateral ties, also you will have some steel section in order to increase the strength of the column, and this will be mainly used when the load acting on the structure is very much high. And the load acting on the structure is very much high, we will go for such kind of columns. You can see here, if the load to be carried is very heavy, structural sections are provided as reinforcement. Such a column is called as a composite column. Here you can see this is a standard hot rolled I section. The I section will be provided here, and the remaining part will be poured by concrete. Now the next one is tubular column. Tubular column means here there will be the main reinforcement, that is your axial frame bar. Then there will be steel stirrup, that is your transverse reinforcement. There will be a steel tube encasing this. There will be a steel tube, and we will be putting this formwork. There will not be formwork, we will be having only steel tube, and the concrete, the main reinforcement and the transverse reinforcement will be poured inside this. See, this is an elevation, 3D elevation, and this is the cross section of this. So this, there won't be any formwork. This will be inside a steel tube, and this will act as a column. Here also it is mainly used because this carries a higher load. Now we need to have some basic understanding of the slenderness ratio. That is slenderness ratio you have studied in your strength of materials. That is the effective length by least lateral dimension. That is effective length. It is the length between the point of contraflexure of a buckled column. For a column, we will call an effective length of a column. That is the point of contraflexure. That is the point of zero moments. And least lateral dimension means if you are having a rectangular column having B and D, if you are having a rectangular column having B and D, and B is where B is less than D, then the B is called as the least lateral dimension. The least lateral dimension means the smallest dimension in the cross section. That is effective length is the lateral slenderness ratio is the effective length divided by least lateral dimension. And the effective length is given in page number 94 of your IS 456 2000. That is, you can see in page number 94, table number 28, the effective length of a compression member. You can see, and the degree of end restrained compression members. Here, effectively held in position and restrained against rotation in both ends, which means this is being fixed at both the ends. This is one support, this is another support. The column is fixed at both the ends. Then the point of contraflexure or your effective length theoretical value is 0.5 L. The theoretical value is 0.5 L. And your recommended value for design or the recommended value for effective length is 0.65 L. This is because you won't achieve 100% fixity at the ends. There you cannot achieve 100% fixity. As a result, the code says the theoretical value, this is based on Euler's equation. The code says the theoretical value, and it is recommended to use this value for the design purpose. That is, due to partial fixity, you won't attain full fixity here. The second one is effectively held in position at both ends and restrained against rotation at one end, which means it is effectively held in position but not restrained against rotation at one end, which means one end is hinged and the other end is fixed. Other end is fixed. You can see here, effectively held in position at both ends. It is held in position, restrained against rotation only at one end, which means one end is not restrained against rotation. So it is free to rotate here, which means this is a hinge. So the theoretical value is 0.7 and recommended value is 0.8 L. Similarly, you can see effectively held in position at both ends. It is effectively held in position but not restrained against rotation, which means this is a free to rotate, which means these two ends are hinged. Then the theoretical value of effective length and this is same because your point of contraflexure will be the length of the column itself. So here theoretical value or your effective length is L and the recommended value is also L. Now these are unbraced columns. That is, this has an effect. If you are applying a load, it can move in this way. This is held in position at one end and restrained against rotation at one end. We are providing effectively held in position and restrained against rotation at one end, and the other end restrained against rotation but not held in position, which means it can move in this way. So here also the recommended value is theoretical value is 1 and recommended value is 1.2 now. These are braced columns actually. You don't have the design for these columns. Now the next one is here. This is actually a cantilever, effectively held in position and restrained against rotation at one edge and not in partially restrained against rotation but not held in position. This is 1.5 L. Sorry, this is actually some restraints are provided this. Now the last one, you can see this is also similar kind. The last one is the cantilever, that is effectively held in position and restrained against rotation at one end but not held in position nor restrained against rotation at the other end. Here the effective length is 2. So keep in mind, you'll mostly cases you will be having the first three cases. That is, you are actually designing a braced column. You'll be having the three cases, and in examination you can come across, that is in some of the public examinations, your gate examination, your PSC, this value can be asked, the recommended and theoretical values for effective length based on these conditions, that mainly 1, 2, 3 and the last one. So based on the slenderness ratio, you can see here, based on the slenderness ratio means effective length by least lateral dimension. This is the effective length you will get from your page number 94 of your IS 456 2000. You can see there is a classification of the column. This is the schematic representation of what you have seen. That is, when you are applying a load like this, the point of contraflexure will be this much distance. That is, your effective length is L is equal to 2 times your length. That is what you have seen here. Effective length is 2 times of your normal length of the column. If both ends are pinned, then effective length is L is equal to L, because your point of contraflexure will be this distance. One end is fixed and other end pinned, then effective length is 0.7 L, and both end fixed, that is your point of contraflexure will be this distance, because here will be hogging and here will be sagging, so your distance is L is equal to 0.5 L. This is some schematic representation of this thing. Okay, so here you can see, based on the slenderness ratio, there are three cases. That is, lambda less than 3, then it is called as the compression member is called as a pedestal. When the lambda value is between 3 and less than or equal to 12, it is called as a short column, and when lambda is greater than 12, it is called as a long column. So we will discuss one by one. The first one, when lambda is less than 3, it is called as a pedestal. There is no reinforcement provided, only PCC, that is plain cement concrete, is provided for a pedestal. You can see here, this you might have seen in your railway station. You might have sit over here. This is a compression member. This is taking compression, and the effective slenderness ratio less than 3. Here we are providing only PCC, but minimum reinforcement of 0.15% will be provided. That is recommended by your IS 456-2000. So this is called as a pedestal. That is, this is mainly used for taking the compressive load, for effectively transferring the load which is coming from this structure to this footing, or through the concrete it will be transferred to the footing. You can see here, see, this is called as a pedestal. It is actually taking the compressive force, but the length or the height is very much small. So the code recommends, in case of pedestal, which is the longitudinal reinforcement is not taken into account in strength calculation, that is, we will not, this is considered as a PCC, there is no strength calculation, the reinforcement is not taken, but the nominal longitudinal reinforcement not less than 0.15% of the cross-sectional area shall be provided. You can see this in clause 26.5.11 H. There you can see in IS 456-2000, you can see this. That is, the minimum reinforcement provided for a pedestal is 0.15% of the cross-sectional area. So keep this in mind. This can also be asked for your competitive exams. Okay. Now the second one, short column. That is, when lambda is greater than 3 and less than or equal to 12. Columns with low slenderness ratio, that is relatively short and stocky columns, invariably fails under ultimate load with the material, that is your concrete or steel, reaching its ultimate strength and not by buckling. That is, when the length is very much high compared to your cross-sectional area, there is a chance for buckling. You can imagine, like, you are taking a thin element, you are taking a suppose you are taking a chalk piece, and you are taking a refill, you are applying a force. What will happen? Definitely the refill which is having the pen refill which is having small cross-sectional area when compared to the length will buckle, and the chalk will get compressed. The same thing is happening here. So for a short column, the column fails by compression mainly. You can see here this is a short column. When compared to the cross-sectional area, the length is not that much high. That is, lambda is less than or equal to 12. You can see here this is a short column. Then it ultimately fails by crushing of the concrete. As you can see here what happens, the reinforcement is still there, but the concrete here has crushed. The concrete here has crushed, or this has failed by crushing of the concrete. That is, according to IS 456, for a short column, LEX by D and LEY by B must be less than 12. This and is very important. That is, LEX means effective length divided by lateral dimension, and LEY, I told you, lambda means what? That is your slenderness ratio, means effective length by least lateral dimension. Effective length in, if I am taking in x direction, then the least lateral dimension is D, and if I am taking y direction, lateral dimension is B. So here I'll discuss that later. So here you can see, according to your code, a short column means when LEX by D and LEY by B must be less than or equal to 12. Okay, this is equal to 12. Next one, that is long column. When lambda is greater than 12, then it is called as a long column. You can see here the length is very much high when compared to the cross-sectional area, cross-sectional dimension. These are examples for a long column. You can see here these are long columns. This is having around 3-story normal building height. So columns with very high slenderness ratio are in danger of buckling, accompanied with large lateral deflection under relatively low compressive loads and thereby failing suddenly. So you can see here this happens. See, the last one, it happened by crushing. Here this column has buckled. You can see here there is some deflection here. This is called as buckling of reinforcement. This column failed by buckling actually. There are some other issues also, because you can see the concrete is not good here, but ultimately the column failed by buckling. Here for a long column, LEX by D, or you can see here this or LE by B must be greater than 12. That is, in any direction, if this slenderness ratio is greater than 12, then the column can be called as a long column. Now, based on the type of loading, columns with axial loading, that is applied concentrically, you can see here the column, the load is being applied exactly at the center axis, then it is called as a then it is called as column with axial loading. You can see here there is no eccentricity here. The second one is column with uniaxial eccentric loading. You can see here this is your axis, there is an eccentricity in one of the axes. As a result, there will be axial compression and uniaxial, that is in any one axis there will be bending occurring. And column with biaxial eccentric loading, that is there is eccentricity in both axis. This axis, if we are taking this as EX, that is eccentricity in X direction, and this is eccentricity in Y direction. There is eccentricity in both directions. There is the bending will take place in both the axes. That is called as column with biaxial eccentric loading. And in real case, and here in your this semester you have only your studies are limited to column with axial bending, and in next column with axial loading, and in the next semester the first module deals with the column with uniaxial eccentric loading and biaxial eccentric loading. So in real case, you can see here this is actually the cases what he has said. Here see this column. This column is taking load half from here, half from here, half from here, and half from here, which means the moment which is created in this direction is counteracted by here, this moment in this direction. If the loading condition and this stretch, all these things are same, the material used, everything is same, then the loading coming here will be counteracted by the loading coming over here, and the loading coming over here will be counterbalanced by the loading coming over here, which means this will be, the load will be acting exactly at the axis of this column. As you see here, so this I can call it as a axial compression member. As you can see, this is the first case, axial compression or column with axial loading. The second one you can see here, this actually the load over here in this direction it is balanced, but here you can see there occurs a bending. There is an eccentricity of load over here, that is because the load will be acting over here. As a result, this will be bending in one direction. Here this corner column, you can say there is eccentricity over in this direction, there is eccentricity over this direction, there is no balancing of the load. So this is column with biaxial bending. So I can say every corner columns will be having biaxial bending. Every edge column will be either having uniaxial or biaxial bending, and interior columns with the loads or the materials used are same, it will be axially loaded. Now braced column and unbraced column. This is called as a braced column. That is, if I am applying a horizontal load like this, the reflection will be very much small. This mainly affects when there is a wind load or an earthquake load. You can see here. In most of the cases, columns are also subjected to horizontal loads like wind, earthquake, etc. If lateral supports are provided at the ends of the column, then the lateral loads are borne entirely by the lateral support. That is, this will take the entire lateral loads. Such columns are known as braced columns. When relative transverse displacement between the upper and lower end of the column is prevented, the frame is said to be braced. That is, if this is prevented, the relative motion of these two are prevented, then this column is called as a braced column. This will be more effective when there is a wind load or earthquake load. And most of the frame structure, we can say this is a reinforced concrete structure. We can say this is it is a braced structure because there is bracing due to the fixity of the slab and the column, the beam and the column. And unbraced means when you are applying a load, there will be large deflection. You can see here the columns where the lateral loads have to be resisted by them in addition to the axial loads and end moments. are considered as unbraced columns. That is, this has to resist more load when compared to this one. You can see in page number 94 of your IS 456, that is, I have discussed this one. These three cases, 1, 2 and 3, these are braced columns, and the remaining are unbraced columns because it cannot resist lateral loads. So we need to provide extra reinforcement in order to resist the lateral loads. So here we will end today's session. That is the basics of your column design. The next class we will start with the coiled provisions and design of a axially loaded column. Thank you guys. Have a nice day.